what we found is that the work done by gravity, as the object is coming downwards, is equal to mgh. Or a little bit more generally, mg times the difference in height. What's the amount of height that the object came down? In other words, we might say the initial minus the final height. If we multiply this out, this would give us mghi minus mghf, initial height, final height. The work done, we know from the work kinetic energy theorem, is equal to the change in the kinetic energy, or kf minus ki, so that this is equal to this here, mghi minus mghf. Let's bring the ki over to this side and the mghf over to this side. And what do we have? We end up with kf plus mghf is equal to, bring this over here, ki plus mghi. This is a very, very interesting result. Again, we find the same thing on this side as this side, except over here it's evaluated finally, while over here it's evaluated initially. There's this quantity that is the same at the top of the hill as it is at the bottom of the hill. This total quantity. But this part is decreasing. Up here, this one. Up here, this is very large. At the top, this is large. While at the bottom, this height is small. Well, if a small plus something has to equal a large plus something, then this one must be small, while this one must be large. So what happens? As the skier goes down the hill, what happens? Their kinetic energy initially is small, but as they go down, they speed up, going faster and faster and faster, so that their final kinetic energy is large. We might think of this as this quantity is turning into this quantity. So this side is kind of turning into this side. As I mentioned before, this is the idea of potential energy. When the skier is up at the top of the hill, they have very little kinetic energy, energy of motion, but they have a lot of potential energy. In other words, stored up energy. Where is this energy stored? Remember, we talked about the energy stored in the spring. In this case, it's stored in the gravitational field. As they were perhaps lifted up the hill on a ski lift or something like that, they were increasing their potential energy. So they have lots of potential energy up here, but very little kinetic energy. As they slide down, what happens? Their potential energy decreases, and that energy gets turned into kinetic energy, so that the sum always stays the same. This is a very, very interesting result. This type of potential energy is another kind of potential energy. We talked about the potential energy in a spring. This is gravitational potential energy. And again, we'll use the symbol U for this. It's still a potential energy, so we'll use U. But let's remember, this is a different potential energy than the one stored in a spring. What do we find? We find that the kinetic, whoops, I won't put KE, I'll just say K. The K final plus U final is equal to K initial plus U initial. In other words, the K plus U is constant. Its value doesn't change. The sum of the kinetic plus potential energies is what we call the mechanical energy. And what we see here is that the mechanical energy is the same finally as it is initially. The total mechanical finally is the same as it started out. It ends up with the same value it started out. This this result is a very, very important result. This is called the conservation of mechanical energy. Let's keep in mind, where did this come from? We made the assumption that there was no friction acting on the object. That's a kind of a general statement. There are a number of different forces that we assume did not act on the object, friction being just one of them. We'll talk about that next time, about what specific assumptions we are making. But right now, let's just think about this. That what we have is a very, very important result. That if we can ignore friction and any other kind of forces like friction, then we end up with a situation where the mechanical energy at the beginning and the end stay the same. When we say that something is conserved in physics, what we mean is that its value does not change. Whatever it starts with is the same as it ends up with. So whatever value of mechanical energy the skier starts with is the same value of the mechanical energy that the skier ends up with. This is a very, very powerful result. Let's stick some numbers in here. Let's try an example with the skier, and we're going to use conservation of mechanical energy to solve this problem. Let's imagine that we've got a skier up at the top of a hill, and she's just gotten off the ski lift. She gives herself a push to get started, and let's imagine that she starts off with some initial speed of 1 meter per second. And then she skis down the hill, a total drop of, let's say, 100 meters. So she's 100 meters higher up here than she is down here. Let's see if we can figure out what is her final speed at the bottom of the hill. Now, could we solve this using Newton's laws? Well, to solve this using Newton's laws, we would have to know what her acceleration was at every point on the hill. And we would need to know a mathematical form of what the hillside looked like to be able to calculate the acceleration, or else at least some very detailed plot of it so that we could do some kind of numerical analysis. But as long as we can assume that there's no friction, or at least friction is negligible, then we can actually solve this not with Newton's laws, but with the conservation of mechanical energy, and it'll be much, much easier. So what does the conservation of mechanical energy tell us? It tells us that the mechanical energy final is equal to the mechanical energy initial. In other words, the kinetic final plus the potential final is equal to the kinetic initial plus the potential initial. So initially, what do we have? Well, we've got her initial kinetic energy, which will be 1/2 mv squared, mass is 60 kilograms, times v, initial v is 1 meter per second. So remember, kinetic energy, 1/2 mv squared, plus her initial potential energy. So potential energy, gravitational potential energy is mgh, which is 60 kilograms, times g, 9.80 meters per second squared, times h, her initial height is 100 meters. The bottom is 0 meters, her initial height is 100 meters. Hope you can see this, I'll put it here, 100 meters. So what do we get? Well, we multiply this and we get 30 joules, kilogram meter squared per second squared. 30 joules, that's her initial kinetic energy. What's her initial final? 60 times 9.8 times 100, that is 5.8. 5.88 times 10 to the 4th joules. Adding 30 to that, well, it's kind of insignificant compared to this big number, so we end up with the same, 5.88 times 10 to the 4th joules. Her initial speed of the 1 meter per second really doesn't contribute all that much. All right, this is her initial mechanical energy. This must equal her final mechanical energy, which is her final kinetic, which will be 1/2 mv final squared, plus her final potential. What's her final potential if she is at a 0 height? mgh will be mg times 0, which will just be 0. So her final potential is 0. We can find her final speed then by just equating 1/2 mv final squared with the 5.88 times 10 to the 4th joules. In other words, V final will be, we multiply by 2 times 5.88 times 10 to the 4th joules, divided by m, which is 60 kilograms. And then that gives us Vf squared, so to find Vf, we take the square root. And multiply that out, and what do we get? We get 44.3. Let's see, these units work out. A joule is a kilogram meter squared per second squared. Divide off a kilogram, we get meters squared per second squared. Take the square root, and we end up with meters per second. Excellent, that works right out. Meters per second. There we go. Her final speed is, or velocity in that direction, is 44.3 meters per second. We were able to solve this very, very easily without any specific knowledge of what the hillside looked like, assuming there was no friction. Okay, very, very good. This is a very, very powerful tool that can be used to solve different kinds of problems. Here we only used the gravitational potential. Let's try one more problem where we use both potential energies that we have talked about. Here we have a mass on a spring. Let's imagine we have a 2 kilogram mass on a spring with a spring constant of 300 newtons per meter. It's attached to the ceiling, so the top is not moving. And let's imagine that we displace it upwards by 5 centimeters from its equilibrium position. So if the mass were just allowed to hang still, it would hang right here at this 0 point. But we're going to move it upwards by 5 centimeters, and then we're going to see what happens. Well, what's it going to do? It's going to start to fall. First, let's figure out what will its velocity be as it passes through the equilibrium point. As it passes through 0, what's the velocity? Well, we're going to solve this not using Newton's laws. We're going to solve it using conservation of mechanical energy. So we will have the mechanical energy at this point should equal the mechanical energy at this point, at the bottom. Well, what kind of mechanical energy do we have? We've got kinetic, so it would be the initial kinetic. We've got a spring, so we'll have the spring potential energy. But then it's also moving vertically, so we'll have gravitational potential as well. So U gravitational, so I've got U spring, U gravitational, both evaluated initially. And then let's figure out what is the mechanical energy as it passes through equilibrium. It will be the kinetic energy, K final, plus U spring final, plus UG final. Okay, there we go. So, what kind of energies do we have? First of all, let's imagine that it is released from rest. So what is the initial kinetic energy? 1/2 mv squared. If it's released from rest, initial velocity will be 0. So that one is 0. And then as it passes through equilibrium, what is the spring potential energy? Well, 0 displacement, it will be 0. So this will be 0. And assuming that we set our height, our our 0 level height at equilibrium, the final potential will be 0. So we're starting out with potential energy in the spring and gravity up here, and it's turning all into kinetic down here. So what is the initial potential going to be? Well, the initial spring potential, what's the spring potential energy? 1/2 kx squared. So that will be 1/2 times k, which is 300 newtons per meter, times x, 5 centimeters, 0.0500 meters squared. So 1/2 kx squared plus mgh. M is 2 kilograms times g, 9.80 meters per second squared, times h, and we are 5 centimeters above equilibrium. 5 centimeters times 5 centimeters. Okay, we multiply that out, and what do we get? Well, I'll just put the products up here. We get for the spring potential energy, we get 0.375 joules. And the gravitational potential, we get 0.980 joules. There we go. Adding them together, we have a total initial mechanical energy of 1.355 joules. There we go. That must equal our final kinetic, which is 1/2 mv final squared. Well, m is 2 kilograms times v final squared, which we can then equate, because we know the initial mechanical equals the final mechanical. This must equal 1.355 joules. So we've got 1/2 times 2 is 1, divide by kilograms, take the square root, and what do we have? We have V final equals 1.16 meters per second. There we go. Okay, very good. There's our final speed as it passes through equilibrium. Let's try one more. Let's imagine that the mass continues until it finally comes to rest. So somewhere down here, we'll say at some distance x from the equilibrium, some displacement x, it comes to rest. How far down does it go? Does it go down 5 centimeters like it started up 5 centimeters? Does it go down another 5? Let's figure that out, see what we get. Well, we know what the initial mechanical energy is. That's still the same. Let's now set our final down here. So we've got a new final position. That is again going to be K final plus U, what do we do first? Spring final plus U gravity final. Now we're looking for the point where it comes to rest. So where is that? What happens there? What's the final kinetic energy at that point? Well, if it's coming to rest again, that's going to be 0. So we can ignore that one. So what do we end up with? What is the final spring? Well, what's the spring potential energy? It's 1/2 K x squared. Well, we actually called it x, so it'll be 1/2 times K, 300 newtons per meter, times x squared, plus the gravitational. Now, we are a distance x below our 0, so our potential is going to be negative. We can have a negative potential energy if we are below our 0 height. We can set our origin, our 0 height, anywhere we want. If we're above that, we have a positive gravitational potential energy. If we are below that, we have a negative gravitational potential energy. That's okay. We can have negative energies, in particular negative potential energies. We can't have negative kinetic energies, but we can have negative potential. So what will we have? We'll have minus mgx. So minus m, 2 kilograms, times 9.80 meters per second squared, times x. And again, our final mechanical must equal our initial mechanical. This must equal 1.355 joules. Well, how are we going to solve this? We're going to have to solve this using the quadratic. We've got an x squared and an x term and a constant term, so we're going to have to solve this with the quadratic. Let's simplify a little bit. We've got 1/2 times 300, or 150 newtons per meter, x squared, minus, let's multiply 2 by 9.8, and we get 19.6 kilogram meters per second squared, times x, bring this over to the other side, minus 1.355 joules, and all of this must equal 0. Okay, what a mess for the quadratic. How are we going to solve this? I'll see, hopefully you can see it over here. What we'll have is x equals the opposite of b, so 19.6 kilogram meters per second squared, plus or minus the square root. Okay, I'm going to have to move this over here. B squared, 19.6 kilogram meters per second squared. So B squared minus 4 times A, 150 newtons per meter, times C, which is negative 1.355 joules. Okay, notice the negatives cancel. That square root goes over this whole thing, and then divided by, the whole thing divided by 2a, which is then 300 newtons per meter. There we go. Doing the first term, this is plus or minus, sorry. So this over the 300 newtons gives us 0.0653 meters. And then plus or minus the square root term over the 300 meters gives us 0.115 meters. If we add them together, we get 0.180 meters. If we subtract them, we get negative 0.050 meters, only to 3 decimal places. In other words, 18.0 centimeters or negative 5.0 centimeters. Well, let's think about that. Negative 5.0 centimeters, what does that mean? Well, negative 5, if this is the positive direction, negative would be up here. Negative 5, well, that's exactly where we started. That's exactly what we would have expected. Of course, the situation up here should match exactly the initial mechanical energy because that is the initial situation. So, the fact that we actually get that as a solution is a good sign. 18 centimeters, so what does that mean? That our mass will drop 18 centimeters before it comes to rest. Quite a bit more than the initial 5 centimeters. Does that make sense? Well, yeah, because if there were no gravity, it would extend exactly the same distance below, 5 centimeters. But because we have now also given the mass this much gravitational potential, it's still going to be moving down here. This will be the point where the potential energy of the spring is matched the initial potential energy of the spring. But we have now added this much gravitational potential, so it's still going to be moving down here enough to carry it down so that the spring potential energy has to take that much more energy out of it in addition to that much more gravitational potential energy until it finally comes to rest at a total distance of 18 centimeters below the equilibrium point. In other words, 23 centimeters below its initial point. All right, very, very good. That was quite a complicated problem where we had not only kinetic energy, but 2 kinds of potential energy. Next time, we're going to go back to our definition of work and see how we can use that to understand how in general can we define these potential energies. What do we need to do to define a potential energy, and what kind of forces will and will not define potential energies. See you next time.